So in this video, we're going to take a little break from quantum protocols and see how we can work around the impossibility result for bit commitment that we saw in the previous video by instead relying on computational assumptions. So let's make one important computational assumption, which is that we have access to a function, a classical function, which maps n-bit strings to 3n-bit strings such that this function g is a pseudo-random generator. What this means is that given the output of g, when g is evaluated on a random string, no adversary can distinguish this output from a uniformly random 3n-bit string. So of course, statistically this is impossible, because if the input is an n-bit string, the output only takes 2 to the n values, not 2 to the 3n. So of course it's very different from a uniformly random 3n-bit string. But our assumption is that no reasonable adversary, in the sense that no computationally bounded adversary, will be able to distinguish between the output distribution of g and a uniformly random 3n-bit string. That's an assumption. Let's make the assumption, and under that assumption, give a secure protocol for bit commitment. So how does the protocol work? There's two phases, commit and open. So in the commit phase, Alice has to commit to b. But here's how it's going to work. Bob is actually going to send the first message. So what Bob does is he chooses a uniformly random 3n bit string, r, and sends it to Alice. Now on receiving r, Alice chooses a uniformly random string s that has n bits, n, and she sets sigma to be equal to b times r plus g of s, okay? So b is just a bit. So what I mean here is that this b times r is either the all zero string or the string r. That's 3n bits, and she takes the bitwise parity with the output of her pseudo-random generator on the string s. She sends that to Bob, sigma. That's the end of the commit phase. Now how about the open phase? This is simple. Alice is just going to send s over to Bob, and Bob will compute sigma that he received plus the pseudo-random number generator, g of s, and he'll check that this is either the string r that he had or the zero string. And if he sees r, then he'll set b to be equal to 1. If he sees 0, he'll set b to be equal to 0. Let's call it b prime, in case this might not be the same as Alice's bit, and he outputs b prime. So that's the totality of the protocol. Let's check it. Is it correct? Correct, yes, because if they do what they're supposed to do, by definition of sigma, when Bob takes the parity with g of s, the g of s cancel out. He's left with either r, in case b was 1, or the 0 string, in case b was 0, and so he outputs b prime equals b. So the protocol is correct. This passes. How about security? So for the security of bit commitment, there are two properties that we need to verify: that the scheme is hiding and that the scheme is binding. Let's first check the binding property because it's easier and it doesn't need the computational assumption. Reason is that if you look at the reveal, the open phase of the protocol, then what's the chance that Alice is able to open two different inputs? Well, once she's committed to a certain sigma, then if she wants to be able to open both b prime equals 0 and b prime equals 1, she needs to find two different s, s0 and s1, such that g of s0 plus sigma would be equal to 0, and also g of s1 plus sigma would be equal to r. But now r has been chosen uniformly at random, and g maps n-bit strings to 3n-bit strings. So the chance that this is possible, meaning the chance that you could get the parity of g of f0 and g of s1 to be equal to r, is only going to be about 2 to the n divided by 2 to the 3n. So the chance, this will only happen with probability about 2 to the minus n over the choice of r. And so as long as Bob chose this r honestly, meaning uniformly at random, then there's very little chance statistically that Alice is able to find that there even exists two strings s0 and s1 that would let her open two different bits. So the binding property holds statistically. Now the hiding property is going to rely on the computational assumption. The reason is that the scheme will only be hiding in as much as Bob cannot tell the difference between a sigma that was generated as g of s or a sigma that was generated as the parity of g of s and r for r that he holds. Meaning that the scheme will only be secure in as much as Bob cannot tell the difference between a uniformly random distribution and the output distribution of the pseudo-random generator. So you can show that the hiding property of this scheme directly reduces to the security property for the pseudo-random generator. So as long as the pseudo-random generator is secure, the scheme is secure. Of course, we need a pseudo-random generator, and you can build these based on standard computational assumptions. For instance, if you assume that there exists one-way functions, then you can compute a PRG. So this gives us a computationally secure implementation of bit commitment, which, given the impossibility result that we saw before, comes close to the best that we could hope for. The other option is to make physical assumptions to achieve security. We'll learn about these next week.